Welcome to ALP Chemistry on Video, and this is a lesson on matter. So at this point, we've already looked at what chemistry is. Chemistry is the science of matter. A science we've looked at as a method, a way of discovering and learning. And chemistry being the science of matter, we want to look at what matter is in detail. So that's what this unit is about. So matter is, I like to say, anything that is a thing. And by that, we mean anything that is a physical thing. So we're talking about physical stuff, stuff that has substance in the physical world. So how do you know that something is matter, that it has physical substance? It is matter if it has mass and volume. Mass being the amount of material in something, and volume being the amount of space the object takes up, or the substance takes up. You can know something has mass if you can weigh it, if gravity pulls on it, and often we determine an object's mass by weighing it. Another way to determine if something has mass is if it has inertia. So in other words, if it can push on something and move it. So for example, we can know that air is matter because if the wind blows on you, you can feel it. It can push you. So that means it has inertia, it has mass. And you can tell that air has volume because if you blow up a balloon or blow up a car tire, fill it with air, then the amount of room it takes increases. So you know it has volume. So let's look at weight versus mass. So this is the amount of matter that is in something. That's what mass is. So that's mass. And like I say, weight is the pull of gravity. So technically, they are different. Although on Earth, we really don't distinguish between weight and mass very much because we often determine something's mass by weighing it, by determining its weight, the pull of gravity. However, if you were to take an object into space, then its weight and its mass might be different. So if you put something in orbit, um, it may not weigh anything. It may appear to be weightless, but it will still have mass because it still has matter and it will still have inertia. If you go to the moon, then the object that you take from Earth to the moon won't change its mass, but its weight will change because the pull of gravity on the moon is different from the pull of gravity on Earth. In practice on the Earth, we don't really distinguish very much between mass and weight. And on Earth, we usually determine mass um, by measuring the pull of gravity on Earth, in other words, by its weight. So we usually determine mass by measuring the pull of gravity, and we call that weighing. And usually what we're looking for when we weigh something is to determine its mass. So in practice, when we weigh, we're determining the pull of gravity, but what we really want to know is something's mass. And on Earth, we usually don't distinguish between the two, but like I say, if you go to the moon or go to Mars, then they might be different. So let's look at some examples of things that are matter and are not matter. So if we want to know if something is matter, then it will have to have mass and volume. So anything that has mass or volume will be matter. And there are lots and lots of examples. If you look around, you can probably find some things that are matter immediately. So for example, If you see a piece of paper in front of you, that's matter. If you're holding a pen or a pencil, that would be matter. The desk that you're sitting at, the chair that you're sitting on, all of those would be matter. So anything solid would be matter. And those are immediately obvious, but also liquids are matter. So if you have a drink in front of you, if you have water in front of you, or coffee, then that is matter as well. So liquids are matter. They take up space. So when you pour one into a cup, you can see, or glass, you can see that they take up space in the cup or the glass. If you take a shower, you can feel water push on you, so it's got inertia, and gravity pulls on it because it falls to the ground or falls to the bottom of your shower or your tub. Gases are also matter. So for example, helium that you might put in a balloon is matter. And it may not appear to have weight because it's less dense than air and floats. So weighing helium can be a bit difficult, but it is definitely matter. When you put helium into a balloon, you can see it takes up space. The balloon increases its volume. Oxygen is a gas that you're breathing right now. We need oxygen to live, and oxygen is definitely matter. It has mass and takes up volume. In addition to all of these things, um, uh, living systems are matter. So, for example, bacteria would be matter. Um, animal animal tissue cells, animal cells or plant cells would be matter. So that's living matter. But these things, again, have mass, take up volume, so they would be matter. So there is an interesting question about humans, and sometimes when I'm asking students to give examples of matter, they say human beings. And I question that a little bit because are human beings more than just physical substance? So our bodies are definitely matter, but are our bodies all that make us human? And I might argue that that isn't the case because you could have a human body that is not living, and so it doesn't uh, represent a full human being. So there's more to us as humans than just our bodies. So if you think about some of the things that make us human that don't have mass or volume, they might be a little difficult initially to think about. But in fact, your thoughts are not matter. They're important. They are what help to make us human, but they don't have mass. They don't take up space. So thoughts are not matter. And similarly, ideas that you might have are not matter. Anything that happens in your brain, so feelings and emotions, for example, are also not matter. Some other things that aren't matter um, are memories. There are other things that physics and chemistry are interested in that are not matter. For example, energy. So energy doesn't have mass and doesn't not have volume, does not take up space, but it is something that can be studied. And different forms of energy um, also not matter. So for example, light. Light is a form of energy, does not have mass, doesn't take up space. In fact, whether light has mass or not is a bit complicated. So physicists might talk about rest mass versus mass in motion. So it can be a little bit complicated, but for practical purposes on Earth, we don't think of light as having mass or taking up volume. So we don't think of light as being matter. Sound, in fact, is a form of energy and it passes through matter. So sound passes through air and can pass through water and can even pass through solid objects. But it doesn't have mass, does not take up space. Something else that is important to us but doesn't have mass or volume is time. So time is important because you need to know if you have enough time to do this lesson today or not. You need to know what time your next class is going to be. So time is important to us, but it doesn't have mass or volume. So things that are not matter, it's not that they're not important, it's just that chemistry doesn't focus on them. There may be other topics or other areas of study that do. So for example, psychology might be interested in thoughts and ideas, feelings, emotions, and memories, and those are very important, but it's just not chemistry's focus. Chemistry is focused on other things. Similarly, light and sound are important to us and to the world, but not necessarily the focus of chemistry unless these things affect matter. So if light affects matter and causes chemical reaction, or there are in fact even some sound initiated chemical reactions, in that case, chemistry would be interested, but it's only in as much as these things affect matter that chemistry is interested in them. And similarly with time, there are some chemical changes that take place over time, some of them very short time, some of them very long time, but it's only in how time relates to matter that chemistry is interested in time. Now, physics is very interested in studying energy and time, but it's just not chemistry's focus, except in as much as these things relate to matter. So when we talk about matter, we need to have ways of talking about matter. And we tend to, in order to help understand things, is to classify them, to break them down into chunks and then talk about each chunk so that we can understand it. So there are different ways to classify matter, to break matter down into um, different ways of talking about it. And one way we can talk about matter is by the properties of matter. And properties, when we talk about properties, we're talking about unique characteristics of matter. And we've already talked about two properties of matter, mass and volume. So those are characteristics, those are ways that we might describe matter. So we might say one object has more mass than another object. And that's a way of talking about matter and distinguishing between matter. So in terms of properties, we tend to talk about properties in two different ways. We tend to talk about physical properties. So physical properties are the physical characteristics of matter. So those are the kinds of things like mass and volume. And that is in comparison with chemical properties, which relate to the ability of matter to change and to form new substances. So we have physical properties and chemical properties. Physical properties being the characteristics, the physical characteristics of matter, chemical properties being the ability to change into and form new substances. So let's look at some examples of some physical properties first. So mass and volume we've talked about. So if we wanted to describe an object by its characteristics, some of the first things that might come to mind is the shape of an object. Is it circular? Is it rectangular? Is it a cube? What is its overall shape? We might also think, what's its color? Is it red? Is it blue? Is it white? Is it black? We might think, does it have texture? Is it smooth? Is it rough? Is it soft? Is it hard? We might think of substance's state. And when we talk about state, what we're talking about is solid, liquid, and gas. That's what we call the state of matter. We could talk about, if we're talking about an object size, we could talk about, for example, how long it is, its length. We could talk about its width. We could talk about its height. So all three dimensions. If it's a circular object, we might talk about its diameter. We might talk about whether we can see through it or not. And that would be a property called transparency. So something that is transparent, we can see through. Something that is translucent will allow light to pass, but not be able to see through it clearly. And by the way, transparency is different from color. Some people will talk about a solution as being clear when they really mean colorless. So clear and colorless are two different things. Clear means it's transparent. You can see through it. Colorless means it has no color. So something can be transparent and still colored. So you could have something that's blue that you can see through. So it would be transparent, but it would be colored. It would be colored blue. But something may also be colorless and clear as well. So it may not have color and you may be able to see through it. So those are actually two different properties. The property of causing something to change from a solid to a liquid. So when something changes from a solid to a liquid, that's called melting. And that typically happens at a specific temperature called the melting point. So melting point is a property of materials. Different substances have different melting points. So for ice, for example, it melts at 0 degrees Celsius. That is its melting point. And in fact, if you go the opposite way, instead of melting, if you freeze it, so in other words, you turn the liquid back to solid, that happens at the same temperature, at 0 degrees Celsius. So it's just a question of which direction you're going. So the freezing point is the same as the melting point, just going in the opposite direction. Instead of going from solid to liquid, going from liquid to solid. Similarly, the temperature at which a liquid turns into a gas is called the boiling point, which is another property of matter. Different substances will have different boiling points. So water, for example, boils at 100 degrees Celsius. So the Celsius scale was created based on water, so that the 0 on the Celsius scale would be at the melting point of water, and 100 would be at the boiling point of water. So there are, let's see what else I have in my list of properties. So volatility. So the ability of a substance to turn from a liquid to a gas. So something that is very volatile will turn into a gas very easily. Something that is not very volatile will not turn into a gas very easily. Some other things, the ability of something to bend would be flexibility. If something can bend easily, it's flexible. If something can't bend easily, then it isn't very flexible. The ability of a substance to conduct heat or electricity, so that would be conductivity. The ability of something to dissolve, solubility. Now, this is one that sometimes causes a little bit of confusion. When you dissolve something to make a solution, um, what's happening there? Is this a physical change or a chemical change? So is solubility a physical property or a chemical property? And what you need to think about is, are we creating a new substance or not? So when you dissolve something, let's say we take salt and dissolve it in water, are we creating a new substance? And in fact, we're really not, because if you let the water evaporate, you could collect the water and it's still water, and the salt you can collect again and it hasn't changed. So you really haven't created a new substance. If you created a new substance, then we would talk about that as a chemical property. But because it's not a new substance, then it's just a physical property. So there are lots of other physical properties, and we just listed a few of them there. There are many, many more physical properties as well. But let's look at chemical properties, being the ability to change into form and form new substances. These can be harder to think about than the physical properties. The easiest way to think about these is to think about some changes where we get new substances, and the ability of a substance to undergo those processes and make new substances would be a chemical property. Or in fact, the ability not to make new substances is also a chemical property as well. So for example, one of the easiest ones to think about is burning. So if you burn something, you actually change a substance into a different substance. So when you burn wood, you don't get wood back at the end of the burning. What you get is carbon dioxide and water and other substances like smoke. So, so burning is a chemical change where you get new substances. And so the ability of something to burn, we call flammability. So flammability is a chemical property, the ability of something to burn. And also, in fact, the ability not to burn. So if something doesn't like to burn, that is also a chemical property. Let's see, what else have we got? So some other processes that relate to changes. So another change would be when you uh, eat food and you digest it and your body processes the food turns into other things. So the food will turn into parts of your body or will turn into waste that we get rid of as pee or poop. So digestion is a process where we get new substances. And so uh, the ability of a substance to be digested would be digestibility. And our food waste, once food that we don't eat and we want to get rid of, we may compost. And when you compost food waste, it turns into fertilizer, new substances. And so we might do that by composting. So something's compostability would be a chemical property. Some of our foods, before we eat them, we actually process them a little bit. And the processing that we do with our foods is sometimes um, controlling the way the food is breaking down. So, for example, when you take grapes and you allow them to decompose in the presence of yeast, you get alcohol and you get a food product which is called wine. And that's called fermentation. So the process is fermentation. So the ability of something to ferment is fermentability, the ability to undergo that process or not undergo that process. Some other chemical properties. Another change is when metals break down. For example, when the steel in a car turns to rust, that is a change where you get new substances, and that process is called corrosion. And so the ability of something to corrode is corrosivity, or the ability of a substance to cause corrosion, we might refer to as corrosivity. Um, Acids are substances which often cause corrosion, and some things, how acid it is, we may refer to acidity. There are some light caused chemical changes called photoreactions, and so a substance's sensitivity to being changed in light we might call photosensitivity. And another interesting chemical property is smell. Now, smell is kind of a tricky one because it sometimes people have a hard time classifying it as a physical property or a chemical property because smell requires that a substance be volatile. It has the physical property of being volatile because the substance has to be able to become a gas so that that gas can then go into your nose and then be detected. But in fact, smell requires the formation of new substances through binding, through chemical binding. What happens is the particles that cause smell go into your nose and stick to certain binding sites in your nose. And those binding sites, there is a chemical interaction there, a binding, where those binding sites trigger nerves in your nose to send signals to your brain that a certain receptor, a certain site has a particle on it, and that triggers your brain to recognize, okay, this binding site, this receptor is active, and that triggers the sense of a smell. So smell is actually a chemical property. Um, what makes smell possible is a substance's volatility, which is a physical property. But you could have a substance which is volatile, which can turn into a gas, but if it doesn't stick to a receptor site in your nose, it will just go in your nose and come back out again, and it won't trigger a smell. it won't trigger your brain to recognize that there is a smell. So in that case, the substance would have no smell. You wouldn't detect it. So smell is actually a chemical property. Okay, so we've talked about physical and chemical properties. In addition to physical and chemical properties, there are also physical and chemical changes. So we have physical changes and we have chemical changes. So what are physical changes? So physical changes are when the state or the properties of a substance change. But when those changes happen, it's still the same substance. So we haven't created a new substance, still the same substance. So for example, if we melt ice and we turn that ice to water, to liquid water, it's still water. So it was water when it was ice. It's still water when it's a liquid. It's still the same substance. So that is a physical change, not a chemical change. Um, and something about physical changes is they're often relatively easy to reverse. So when you melt ice and turn it to water, it's relatively easy to take it from water, turn it back into ice again. This reversibility thing about physical changes and chemical changes is not uh, is an often thing. It isn't a definitive thing. So there are some physical changes which may be difficult to reverse. But if you see a change that is relatively easy to reverse, usually it will be a physical change. If we look at our chemical changes are a change where we do form a new substance. And the composition changes. And when we say composition, what we're talking about is the type of substance and how much is in there. So for example, if we think about hydrogen peroxide turning into water. So hydrogen peroxide is that substance that you may have in your house that is used to disinfect cuts and scrapes. And hydrogen peroxide has the chemical formula H2O2. And what this chemical formula tells us is that hydrogen peroxide is 2 parts hydrogen and 2 parts oxygen. However, if you leave hydrogen peroxide open to the air, it will turn into water. So if you have a bottle of hydrogen peroxide and you don't put the cap on and you just leave it there for a few days, it's eventually going to turn into water. And water has the chemical formula H2O. And what this formula tells us is that water is 2 parts hydrogen and 1 part oxygen. So the process of taking hydrogen peroxide and turning it into water is a chemical change because the numbers of substances, which is part of the composition, changes. So composition is not just the type of substance that is the type of matter that is in a substance, but how much of it as well. And chemical changes are often not easy to reverse. So whereas physical changes are, chemical changes are often not easy to reverse. And again, this is not a hard and fast rule. It's not definitive. There are some chemical changes which are relatively easy to reverse, um, but most chemical changes are not easy to reverse. So for example, if you burn wood, it's difficult to unburn wood and take the products you get from burning and turn them back into wood again. If you blow up a stick of dynamite, it's difficult to take the gases that come out of that explosion and turn them back into a stick of dynamite again. So many chemical changes are not easy to reverse. Many physical changes are relatively easy to reverse. And those are just ways to help you figure out whether something is a physical change or a chemical change. If it's reversible, chances are it is a physical change. And then what you want to do is see if you have the same substance or a new substance. Because if you have the same substance, it's a physical change. If you have a new substance, it's the chemical change. So whether or not you have a new substance is definitive. That will tell you whether it's a physical change or a chemical change. The reversibility guideline is just to help you, but the reversibility guideline is not definitive. So we've talked about properties, we've talked about changes. What's the difference? Because we have physical and chemical of both. We have physical and chemical properties. We have physical and chemical changes. So what's the difference? Well, physical and chemical properties are characteristics. Whereas physical and chemical changes are processes. So the changes are more active. There's something happening. There's something going on. It's a process. Where the characteristic is just a descriptor. It's a way of describing something. It's something's capability. Um, it may be a capability. It may be just a feature that it has. So for example, if we burn magnesium, if we have magnesium has the ability to burn. So this is a property. And we might call that property flammability. So magnesium is actually flammable. It will burn. But until we actually do it, it may not be undergoing the change. So that's the difference. So I have the ability to walk. That is a characteristic. That is a property. But until I do, until I walk out the door, I'm not undergoing the change. I'm not changing my position from where I'm sitting to the door until I actually do it. When I do it, that's the change. I have the ability to do it, which is a property. When I do it, that's the change. So magnesium is flammable, and I do have a YouTube video to go along with this. Let's see if you can see this video here. Let's open it up. Here we go. And so what we're looking at here is a strip of magnesium sitting on a metal can, and it's just sitting on the can so it doesn't destroy my stove where I'm doing this experiment. So I'm going to hold the metal strip with some tongs so that I don't burn myself when the magnesium burns. And then I'm using a little torch to light the end of the magnesium. Little pause here in my computer. Waiting for my computer to catch up. Hopefully will catch up shortly. Okay, here we go. And we've got the magnesium burning. It burns very, very brightly. And in fact, they used to use magnesium in old flash bulbs. So it used to be that flash bulbs were disposable, and you would, if you wanted to take a picture, uh, you would light off a flash bulb and then dispose of the flash bulb when you're done with it. And there is a little bit of white residue left over. That's a new substance. So the magnesium has turned into a substance called magnesium oxide. And so because we have a new substance, it is a chemical change. So magnesium has the ability to burn, which is a property. And when we do it, that's when it undergoes the chemical change. and is a chemical change because we have a new substance. Another example, if we think about melting and melting point, melting is the change. Melting point is a property. So a substance may have the ability to melt, and it may melt at a particular temperature, which would be its melting point. Until we actually cause the change to happen, it hasn't happened. When we melt it, then the change happens. So melting is, do you think that is a physical change or a chemical change? So when you melt something, first of all, is it easy to reverse it? Yes, it is relatively easy to reverse it. And when you melt something, do you get a new substance? And the answer is no. When you melt a substance, it's still the same substance. So melting is actually a physical change. And the melting point is a physical property because we're not talking about turning into a new substance. It's just a characteristic of that particular substance. So some examples of some physical changes and chemical changes. If you think about some things that you do around your home or maybe in your kitchen, chopping and cutting, when you take something and make it into smaller pieces, you're not getting a new substance. Now, in some cases, this may be difficult to reverse. Once you cut something apart, it may not be possible to easily put it back together again, but you don't get a new substance, so it is a physical change. Some other things that you might do in your kitchen, you might be doing some boiling. So boiling is where you turn a liquid and cause it to turn into vapor or gas. You might do some dissolving. So you might take sugar and dissolve it in water or coffee or tea. Um, Evaporation, where you cause something to go from liquid to gas. Um, Freezing, where you take something and you want to preserve it, so you put it in your freezer and freeze it solid. There is something you may not have heard of before. So you know that going from solid to liquid now is melting, and liquid to gas is boiling or evaporating. But there is a process where you can take a solid and turn it directly to a gas without going through the liquid. And that's called sublimation or subliming. So subliming is when you go directly from solid to vapor. And dry ice sublimes. So dry ice is actually solid carbon dioxide, and when it turns into a gas, it doesn't go through liquid, so that's why it stays dry, why they call it dry ice. And so it sublimes. It goes directly from solid to vapor. And freeze drying is actually subliming. So when you freeze dry something, you freeze it solid and then put it under vacuum to pull the water molecules out, to pull the water out, and then cause it to dry. And freezer burn is the same thing. So freezer burn, when that happens, the water comes out of something when it's frozen. So that's a form of sublimation or subliming. The opposite of evaporating is condensing. So if you take a gas, turn it back to a liquid. Phase changes, so we've been talking about phase changes. So all those phase changes or state changes are physical changes because we're not getting new substances. Mixing, when you just mix things together, assuming you don't get any new substances, if you're just mixing things, like if you mix baking soda and flour, um, you have little bits of baking soda in the flour, and they're not new substances. It's still baking soda, it's still flour. They've just been mixed together. Temperature changes. So if you warm something, but it doesn't turn into a new substance, that's a physical change. So in other words, heating and cooling, as long as you don't get new substances, those are physical changes. Let's see here. Crystallization, when you take a solution and cause it to form crystals. Physical change because it's the same substance. And I think I've got everything on my list here. Yep, I got everything on my list. So there could be more. There are definitely more physical changes, but those are some. Chemical changes. Again, if you think of a change where you get a new substance, then that will help you think of some chemical changes. We've talked about burning. We've talked about digestion. We've talked about fermentation and composting. Something else plants do when plants take in light and use that light to make substances. We call that photosynthesis. That is a chemical change because you get new substances through photosynthesis. Respiration, when we breathe and take in oxygen, and that oxygen goes into our bodies and becomes part of our bodies. Cooking. Um, Cooking is usually a chemical process. We usually get new substances. For example, when you cause bread to rise, yeast takes sugar and turns it into carbon dioxide, and you get little carbon dioxide bubbles inside your bread, which is why bread rises. And that's a chemical change. You get new substances. I mentioned TNT and dynamite, so explosions, explosive reactions. I mentioned corrosion, so rusting and corrosion. I mentioned digestion, so one byproduct of digestion is sometimes we fart, and that actually is a chemical change. So flatulence and farting, because some of the substances in our food get converted to gases like carbon dioxide and methane, and that comes out as fart, which is technically called flatulence. Let's see, what else have I got on my list? I think I've covered most of what I have on my list. Maybe some heat-activated chemical reactions. Which actually reminds me of a property that I did not mention, reactivity. So reactivity is a chemical property. So I should go back and add that to the list because there are some substances which will be chemically reactive, and there are some substances which will not be chemically reactive. Properties. So I'm going to add that to our list of chemical properties. So just call that reactivity. So how reactive a substance is to cause a new substance, to create a new substance. Some substances may be very reactive, like um, nitroglycerin, which is very sensitive to and very reactive, and other substances just which are not very reactive. That it's very difficult to get them to be involved in chemical reactions, which is also a chemical property. Okay, so we've looked at many examples of physical changes and chemical changes. We can also classify matter by state. And when we're talking about state, we're talking about solid, liquid, and gas. And there are other states than solid, liquid, and gas. Another one that is sometimes on Earth is plasma. So plasma is like a gas, but it's an ionized gas. It's kind of an electrically charged gas. And to create plasma, you need a very high energy environment. So you may know of plasma torches. Some cutting tools use plasma. Plasma is found in stars, for example. Fire is sort of plasma. Uh, so, um, but plasma is a form of matter we're not really going to talk about in this course so much. It's an unusual form of matter. You need some fairly extreme conditions to generate a plasma. On Earth, mostly what we see in matter is solid, liquid, and gas. So those are what we're going to focus on. If we look at the differences between the different states of matter, solids, we can, if we think about the shape of a solids, solids tend to have a fixed shape. It doesn't change. But liquids can change the shape. So if you pour marbles into a glass, they stay as marbles. If you pour dice into a glass, they stay as cube shapes. If you pour a liquid into a glass, it takes the shape of your glass. Gases can also change, but in addition to changing their shape, they can also expand to fill the container. So if you put a little bit of gas in a part of a container, then that gas can move around the container. And if you look a little bit later, you'll find that gas filling all through the container. So not only do gases change the shape, they can expand and fill a container. In terms of what the particles are doing, in solids, the particles tend to be fixed in place. They don't move. They may vibrate back and forth a little bit, but they don't move past each other. So they stay in pretty much the same spot. In liquids, they move and they move past each other. And that's why liquids can change the shape, because the particles can move and adjust their positions, and then they can take the shape of the whatever object container they're in, because the particles can adjust and move to compensate. Particles and gases move fast, and that's why, because they're moving, they can take the shape of the container. Because they move fast, they can move around the container. Uh, since particles and solids don't really move, they tend to be pretty low in energy. So temperature, in fact, is a measure of how fast the particles in a substance are moving. So if the temperature is low, the energy is low. And if the temperature's higher, then the particles will be moving faster. So that can help you to understand how you turn a solid to a liquid. You put energy in, you increase its temperature, and when it hits the melting point, then those particles will start moving past each other, and then they turn into a liquid. So liquids are higher in energy than solids. So they're in between in terms of energy, solids and gases tend to be very high energy. The particles are moving very fast. In terms of the forces, and when we talk about forces, we're talking about the forces between particles. In solids, the forces between particles are relatively high, relatively strong, and they're so strong that they hold the particles together. That's why the particles can't move past each other, because the forces between particles are relatively strong. In liquids, they're still fairly strong. They're not strong enough to hold the particles from moving past each other, but they are strong enough to hold the particles from flying apart from each other. And in gases, the forces between particles are relatively weak, and that's why the particles can fly apart and expand to fill a container. Packing between particles, or how tightly the particles are packed. Solids, quite tightly packed, because the particle forces are high and holding the particles together. Liquids, they still tend to be quite closely packed because the forces between particles are high enough to keep them together. But in gases, the particles tend to be far apart because the forces are weak and not able to hold those particles together. Consequently, the density of solids tends to be high because the particles are tightly packed. Fairly high for liquids, but low for gases. So gases tend not to be very dense because the particles are quite far apart. Compressibility is the ability to squeeze or compress something, make it smaller. Solids tend not to be very compressible because the particles are already tightly packed and they're going to start bouncing off each other and resisting being squeezed together. So solids tend not to be very compressible, and that's also the same with gases as well. So gases are not very compressible either. Liquids are not very compressible either. So I'm going to move not very compressible between liquids and gases because neither one is very compressible. And in fact, hydraulics work on this principle. So hydraulics are where you squeeze a liquid and the force can be transmitted at a different place from where you're doing the squeezing. So for example, in your car's brakes work by hydraulics. So there's a cylinder under the hood of the car which squeezes your brake fluid, and the brake fluid then gets squeezed through the brake lines out to the calipers at each wheel, and then the force in the liquid can be transferred to the calipers to squeeze your brake discs or drums. However, gases are very compressible, and so consequently, if you get air into your gas lines, what will happen is the air will squeeze together rather than uh, forcing the liquid out to your brake calipers, and so your brakes are going to feel very soft and spongy. They won't work very well. And the last thing is viscosity. So viscosity is how sticky particles are, their willingness to uh, separate from each other. And viscosity in solids and liquids is quite high because the forces between the particles are high, but viscosity of gases is very low. So uh, gas particles are not very sticky. They can flow past each other. If you think about something like molasses, molasses is quite viscous. It has a high viscosity because the particles don't slide past each other very well. So those are differences between the states, solid, liquid, and gas. We can also classify matter by composition. And when we talk about composition, we're talking about what kind of matter and how much. So if we take matter and we break it apart and break it down into the smallest piece of matter that you can, what you get are elements. So if you substances are elements are substances that can't be broken down chemically. And when we say chemically, what we mean is by interacting with other substances. So if you bring two substances together and one of them falls apart, um, that's what we're talking about here. And elements can't be broken down any further. You bring an element next to another substance and it won't fall apart anymore. Now, elements you can break down into smaller pieces, but it typically takes a lot of energy to do it. The kind of energy that's in a nuclear reactor or in a star, for example. Just by chemical interaction with another substance, you can't break an element down any further. So if you have an individual particle of an element, we call that an atom. So atoms are an individual particle of an element. So elements are the building blocks of matter, and atoms are the building blocks of elements. So how do you know if a substance is an element? Well, what you would do is you'd look in the periodic table of elements. If you find it, it's an element. If you don't find it, it's not an element. So the periodic table lists all the elements that we know of. So if it's there, then you'll know it's an element. If it's not there, it's not an element. So if it's not an element, what might it be? It might be a compound. So a compound is a substance made from two or more different elements. And the key for a compound is they have to be different elements. Because if it's the same element, you just have more of that same element. To be a compound, it has to be different elements. And elements are bound together in a compound. So they are chemically bound, they are stuck together. So consequently, composition of compounds doesn't change. Just going to change color on that. So compounds don't change the composition. If you have a change in composition, you end up with a different compound. And that example I gave of hydrogen peroxide, where hydrogen peroxide turns into water, the composition changes. So, and so it turns into a different compound when hydrogen peroxide turns into water. So just like an atom is an individual particle of an element, the individual particle of a compound we call a molecule. And a molecule is a particle that we get by sticking atoms of elements together. So if you have an individual particle of a compound where you have atoms of different elements bound together, you have a molecule, but you can also have molecules of atoms of elements. If you stick atoms of elements together, we still consider that to be a molecule. So you potentially can have molecules of compounds, but you can have molecules of elements as well. So you can have a molecule of an element when more than one atom of the same element are stuck together. So for example, if you have, let's say, oxygen. So what I'm going to do here is use blue circles or to represent spheres of which represent oxygen atoms. And inside we'll put a little O symbol for oxygen inside. And so this represents a molecule of oxygen. And the oxygen that you are breathing right now is in this form. Two oxygen atoms joined together. It's the natural form of oxygen to be two atoms joined together in molecules. And we call this O2. So um, if you've seen anyone that has an oxygen tank that they're breathing supplemental oxygen, often it's labeled O2 because that's how oxygen is found in nature. But oxygen is an element, not a compound. It has the same atoms of the same element bound together, and because you have more than one atom, it's a molecule, but because they're the same kind of atom, then it's an element, it's not a compound. They'd have to be different to be a compound. Now, if we think about water, and we do a similar picture, so we'll represent oxygen again as a blue sphere, and then hydrogens will represent, maybe use a different color, let's say red. So those are meant to represent hydrogen atoms. We use the symbol for oxygen in O in the oxygen sphere. And then we use H's to represent our hydrogen atoms. And I drew them in a V shape because that is the actual shape of the water molecule. So water molecule has two atoms of hydrogen and one atom of oxygen. And it is a compound because it has different elements bound together. So whereas oxygen, it's a molecule because you have more than one atom joined together, but they're the same atom. So it's an element, whereas an individual particle of water is a molecule, but water is a compound because they're different elements. Now, if we take hydrogen peroxide, where we have two atoms of hydrogen again, but now we have two atoms of oxygen, and if we draw this one out, so we have two atoms of oxygen and two atoms of hydrogen. And this is a molecule because you have more than one atom joined together, and it is a compound because they're different elements. And this is a different compound from water because the composition has changed. Instead of having two hydrogens and one oxygen like water does, we have two hydrogens and two oxygens. So if you change the composition, you have a different substance. It's not the same compound. So let's look at some examples. So if we look at hydrogen, which has two hydrogen atoms joined together, is this an atom or a molecule? It is a molecule because it's two atoms joined together. But it's an element because they're the same atom. If we take arsenic, arsenic is an element. You can find it in the periodic table. But here we don't have more than one atom joined together, so it's just atoms, or just an atom. If we go down and look at methane, which has one carbon atom bound to four hydrogens, it is a compound because you have atoms of different elements bound together. And an individual particle would be a molecule because you have more than one atom bound together. So if you have more than one atom bound together, it's a molecule. If they're different atoms or atoms of different elements, then it's a compound. If they're atoms of the same element, then it's just an element. Okay, pure substances. So elements and compounds are pure substances. They're substances where the composition doesn't change. So pure substances are in contrast to mixtures where you have combinations of pure substances, but the composition can change. So combinations of pure substances, they have to be different elements, so different pure substances. Again, because if it's the same pure substance, you just have more of that pure substance. So it would not be a mixture in that case. So if you have some oxygen, you put more oxygen in with it, it's still oxygen. To be a mixture, it would have to be a different substance. So for example, if you put carbon dioxide together with oxygen, those are different pure substances, and putting the two together creates a mixture. When you make a mixture, they're not chemically bound. The substances in the mixture are not chemically bound, like they would in a compound. So in a compound, uh, the elements are chemically bound, they're stuck together. In mixtures, they're not. And because they're not, the composition can change. So in compounds, if you change the composition, you end up with a different compound. In uh, a mixture, you can change the composition and it's still a mixture. So for example, if you take salt and you stir it into water, you could take 1 teaspoon of salt and stir it in. You could take 2 teaspoons of salt, stir it in, 3, and so on. And so you can have different amounts of salt in the water. It is a mixture. You could also do sugar and coffee. So you could have 1 teaspoon of sugar in your coffee. You could have 2. You could have 3 or 4. And it's still coffee with sugar. Sugar in coffee. So those are mixtures. There are 2 types of mixtures, homogeneous and heterogeneous. And the ERIC definition of the difference between a homogeneous and a heterogeneous mixture is whether or not you can see chunks. And by chunk, I mean a difference. So a part of the mixture which looks different from another part of the mixture. So a chunk may not actually be a solid. It may not be a solid chunk. It may just be a part of the mixture that looks a bit different. But for some mixtures, it might actually be a solid chunk in a liquid, for example. But if you can see a difference in one part of the mixture, oops, did I mix those up? Nope, I didn't mix those up. So if you can see a difference in part of the mixture, then it would be heterogeneous. So in a heterogeneous mixture, you can see chunks. In a homogeneous mixture, you don't see chunks. It's the same throughout the mixture. So you look at one part of the mixture, looks the same as every other part of the mixture. But in a heterogeneous mixture, it would not look the same. So for example, a homogeneous mixture, say milk. Your milk should not be chunky. Gasoline looks well mixed. Coffee, you should not see chunks in your coffee unless you have a specialized coffee, maybe an iced coffee with ice cubes in it or something like that. Uh, say pudding, that is completely mixed together. So those are some example of some homogeneous mixtures. Some heterogeneous mixtures, sour to milk might seem a little bit chunky. So if your milk is chunky, then it would be heterogeneous. Uh, so iced coffee, coffee with ice cubes in it, you could see a difference between the coffee and the ice cubes. So that would be heterogeneous. Orange juice with pulp. So if the orange juice didn't have pulp, it would be homogeneous. But if it's got pulp in it, then it would be heterogeneous because the pulp would look different from the juice. Chili would have chunks of meat and kidney beans with the sauce. So that would be heterogeneous. So those are some examples, homogeneous and heterogeneous mixtures. So if we summarize, matter is composed of either pure substances or mixtures. Pure substances where composition doesn't change. And the parts of the pure substance they may be chemically bound. So pure substances and mixtures. Pure substances being either elements or compounds. And mixtures being either homogeneous or heterogeneous. And then a mixture we could break down further into different pure substances. So matter being either pure substances or mixtures, pure substances being elements or compounds, mixtures being either homogeneous or heterogeneous. So we take an example, let's think about seawater without any floaties in it, so no chunks. So it is a mixture. And if it doesn't have any chunks in it, it would be homogeneous because it would be the same throughout. And because it's a mixture, it's a combination of pure substances that are not bound together. And some of the substances in seawater would be water, obviously. Salt, so water being a pure substance. Salt being a pure substance. Oxygen that the fish breathe, which would be another pure substance. There would be many other things in there. So for example, nitrogen and say calcium chloride. Oops, calcium, got to move that over. Calcium chloride. And there would be many, many other substances in seawater in much smaller amounts. So the major substances would be things like water, salt, oxygen, and there'd be many other substances that would be there in much smaller quantities. So we may want at times to be able to take a mixture apart. And because the substances in a mixture are not chemically bound, we may be able to do that. And there are various methods of taking mixtures apart and isolating their pure substances from each other. There are three that are commonly used in chemistry labs: filtration, distillation, and chromatography. We're going to talk about each in a little more detail, but before we do, let's think about other ways that we can separate mixtures. So again, these are some things that we do in our kitchen a lot. So some of the ways we may separate things in our kitchen would be things like boiling, where we would boil off water to separate the water from uh, the food that we're cooking. We may want to boil a sauce down and remove some water out of it. We might sift our flour, and sifting is a separation that works on the basis of different size particles. Another term for that is sieving. So if you sieve something, you separate solids by their particle size. And you can do serial separation. You can separate uh, a solid mixture with finer and finer screens and separate out different fractions by particle size and separate into smaller and smaller particles. So that's a way of doing a separation for solids. Um, we can separate very simply by pouring off. If you have a solid and a liquid, and you may be able to pour the liquid off, or if you have two liquids that aren't mixing, like oil and water, you may be able to pour the oil off the water. So you might be able to do that very simply, or skimming off. If you've got like fat floating on the surface of water, you might be able to skim it off. Basically, any difference in properties you may be able to use to do a separation, and those could be physical properties or chemical properties. So if you can think of any property that could be different between substances, you may be able to use that to do a separation. So for example, density. So if objects differ in density, then you may be able to separate them. Um, and one way that you could do that is put the objects in water. And if some of the objects float and some of them sink, then you could skim the floaties off and leave the sinkies behind. Another property that you could take advantage of is magnetism. So if you have some objects that are magnetic and some that are not, just stir a magnet around your mixture, and things that are magnetic will stick to your magnet, and things that are not will not stick to your magnet. You pull your magnet out, and then you will have done your separation. So for example, when breakfast cereals are enriched with iron, often the iron is added as just iron shavings. They just scrapes pieces of iron and mix them in with the cereal. And you can separate those out using a magnet. If you stir a magnet around a breakfast cereal that is enriched with this form of iron, then you can extract all that iron out and have it stick to the magnet. And our bodies just handle that. If that doesn't sound very good, our stomach acid is very capable of dissolving that iron, and then our intestines can absorb it. So our bodies handle it without any trouble. What else do we use for separations? Um, there is a separation technique you may be aware of where you can uh, spin objects and separate them by how much they get pulled out to the outside, and that's called centrifugation. The device used to do that is called a centrifuge. So centrifugation, spinning. If our kidneys aren't working, then we may need to go to hospital for dialysis. And dialysis is a technique where a barrier with some very small holes is used, and some substances can pass through the barrier, some substances cannot, and the separation is used that way. There's a very similar technique where the holes in the barrier are even smaller so that only water can pass through, and that's called osmosis. And that's how plants get their water, through osmosis. And finally, you can do chemical separations. So chemical separations are where you base your separation on a chemical reaction. So you might have some parts of the mixture which may participate in a chemical reaction and some parts of the mixture that may not. So for example, you may be able to do, if you have a solution where you have two substances dissolved in the solution, maybe one could be involved in a chemical reaction and turn into a solid, and then you can filter out the solid. Uh, Soaps and detergents are actually forms of doing chemical separations. So your soap and detergent molecules bind with your dirt, and then you can use water to rinse the dirt off. So that is actually chemical separation that is happening there when you wash something with soap or detergent. So there are many different ways of doing separations. These three are probably, oops, these three are probably the most common in a chemistry lab. And so we're going to talk about these in a little more detail. So let's start with chromatography because that's probably the one that is least familiar to most people. So the way chromatography works is it uses two phases. One phase we call the stationary phase. It's stationary because it doesn't move. And the other one is the mobile phase because it does move. So the stationary phase could be a solid, it could be a liquid, it could be paper. And the mobile phase is typically a liquid or a gas. It has to be able to move, so we tend not to use solids for a mobile phase. And the way chromatography works is you dissolve your mixture into the mobile phase. You would inject or dissolve it. So you're going to mix, inject, let's say inject your mixture into the mobile phase. And then you pass the mobile phase over the stationary phase. And the separation is based on a chemical attraction of different parts of the mixture to the stationary phase. So if you have a substance that is strongly attracted to the stationary phase, it's going to stick to the stationary phase and it won't want to move through the stationary phase very fast. On the other hand, if you have a substance that isn't very attracted to the stationary phase, it will stay in the mobile phase and it will pass straight through. So the chemical property of different substances to bind to the stationary phase is what will allow you to do the separation. And it works best for homogeneous mixtures. So where the mixture is quite uniform and you can't see chunks in it. And there are different forms of chromatography that are based by name either on the name of the stationary phase, the name of the mobile phase. So for example, um, there is gas chromatography, which uses gas as your mobile phase. Liquid chromatography, which uses liquid for your mobile phase. and paper chromatography, which uses paper for your stationary phase. And chromatography is not very good for separating solids because you have to be able to get the substances you want to separate to dissolve or mix thoroughly with your mobile phase. And if you have chunks of solid, they're not likely to be able to do that. And there are better ways of separating out chunks of solid, which we're going to talk about next. So we're going to talk about filtration, which is how you might separate out chunks, solid chunks. Uh, Filtration is a barrier technique where the barrier is permeable to one part of the mixture, and permeable means it allows to pass. So in filtration, the barrier, the filter, will allow one part of the mixture to pass, but other parts of the mixture will not. So it will be impermeable to other parts of the mixture. And it's good for heterogeneous mixtures where you can see chunks because you can basically separate the chunks out, filter the chunks out. So, for example, water and sand. So you could pour a water-sand mixture through a filter. The water is going to pass through. The sand will be left behind. So water and sand, air and dust. So you have an air filter in your car, and the dust particles are held back on the filter. The air is allowed to pass through the filter. So the simplest kind of filtration that we do in a chemistry lab is called gravity filtration because we just use gravity to pull the liquid through the filter. So in this case here, we have some red solid particles suspended in our green liquid. We pour this through the filter. So the blue in the funnel, so we have a glass funnel here. So we have a glass funnel and we have a filter, which is usually paper that we fold into a cone shape sitting in the funnel. And we pour our mixture through the filter. The liquid goes through, the solid stays behind, and the liquid that goes through we call the filtrate. So you're separating the solid, what we call the filtered solid, from the filtrate. And like I say, there are more complicated forms of filtration where you use, for example, suction to pull the liquid through. But this is the simplest form of filtration. Distillation. Distillation makes use of differences in boiling points. So again, you often use a difference in properties to do a separation. And here the difference is in differences in boiling points. The way distillation works is you want to heat the mixture to evaporate lower boiling point substances. And leave the higher boiling point substances behind. So you're only boiling one part of the mixture. It's best for homogeneous mixtures because if it's a heterogeneous mixture, you might have a simpler technique like filtration or just pouring off. Best for homogeneous mixtures of liquids. So if you have a homogeneous mixture of a liquid that you try and pour through a filter, they just may go straight through the filter. So distillation is a good way to be able to separate liquids. You can also use it to separate dissolved solids. So if you have something that is dissolved in a liquid, you can use distillation for this, um, where you would boil off the liquid, leaving the solid behind. So a distillation apparatus looks something like this. So our mixture is in the flask at the bottom. So our mixture is down here. Again, red particles in the green liquid. You heat your mixture using what we call a heating mantle. So heating mantle surrounds the flask, heats it up. The liquid evaporates, so we have the little liquid particles in the vapor phase that rise up. We have a thermometer at the top just to make sure that we're controlling the temperature of our distillation correctly. Then the particles pass through something we call a condenser. A condenser is usually just a water jacket. So we surround the tube with cold flowing water, which cools down the vapor and turns it back into a liquid again, which then we collect as a purified liquid. And this is what we call a simple distillation. There are more complicated distillation setups. So you may have, in a more complicated setup, you might have multiple condensers at different heights in the column, and you might collect different fractions. So different fractions may condense at different temperatures. So the higher you go up, then the cooler it would be, and the more volatile fractions you would collect higher up in the column. Gasoline is made in this way. So you typically would take crude oil and you would do what they call a fractional distillation. So it wouldn't be just a simple distillation where you're separating off one fraction of the mixture. You would separate off multiple fractions with multiple condensers. And different parts of the crude oil will be purified into fractions like kerosene, gasoline, uh, heating oil, and things like that. But this is a relatively simple distillation, probably the most common kind of distillation that we would do in a chemistry lab. And distillation, you can see, is a fairly complicated setup. And again, this is just a simple distillation setup. So if you have the ability, it's easier to do filtration. Um, so if you have a heterogeneous mixture, just easiest to filter it, or to if it's two liquids that don't mix, if they form layers, you can just pour off one layer. So that's a lot easier than setting up a distillation apparatus and heating things up and running water through the condenser and so on. So if you can avoid doing distillation by doing a filtration, then you would probably do that because it's a lot simpler. And that brings us to the end of the lesson in matter. So the next thing for you to do would be the lab in matter, and the lab for the matter unit is physical change, chemical change lab, and then to work on the assignment. So go ahead and do that, and if you have any questions, then talk to your instructor.